An important quantity, physical quantity associated with light is the brightness or the intensity of the light, how bright it is. We need to make this on a more quantitative basis, and that's and how it's related to waves. But we'll do that in this intensity section. The intensity, and really I'll do just the average intensity, and you can make these deltas become infinitesimal to get the instantaneous intensity. But the intensity of light is the energy that hits an area. I'm going to use not A, but I'm going to use script A for that. Okay. So area script A in time delta T is the area that's hit, the energy that hits in that time period divided by the time delta T. So in terms of symbols, if I have delta E, and I'll use script E for energy in this context, I'll use block E later on for electric fields, so we'll do this form for energy for right now. And then the area A that I hit, that's here, is script A, and then the time is delta T. So that's the definition of intensity. It's pretty obvious if I'm shining a bright light on say a black material, then it absorbs the energy. The light carries energy into it, and this warms up. Right? And this area A, and so the wave is light wave is carrying energy into it, and that's this delta E. The amount it carries in time delta T is here, and the area, of course, that it hits is just script A. The intensity definition, sometimes you see written in a slightly different way. Energy per time, delta E per delta T, is just the instantaneous power. So you may have seen that. Probably should have. And so sometimes you see it defined as the intensity is the power per area, that the amount of energy per time that hits the area A is just the power delivered to it divided by the area. In terms of mechanical waves, you'll sometimes see the power is the work done and the time it was done in. And remember, work is force through displacement, F dx, and this is delta T. And so it becomes a force times the velocity here. Might remember for a simple harmonic oscillator that the total energy of the oscillator is its kinetic energy plus its potential energy. If I have a mass M on a spring with stiffness constant K, then the potential energy is 1/2 kx squared if x measures the distance from the equilibrium position and v is its velocity. One can solve the spring problem, and it just becomes x equals A. I'm using capital A here for the amplitude now. Sine omega t, and then take the derivative of that to get the velocity, so you just get minus A omega cosine omega t. And then omega is the resonance frequency for this mass spring oscillator, which is just square root of k over m. And then oftentimes we can solve this for k in terms of m and omega squared. It's just a constant. But if I plug these expressions in up here, I get 1/2 m times the velocity squared plus 1/2 m omega squared, that's just k, times the position squared. And simplify a little bit, pull out a common factor, and get cosine squared plus sine squared, which is obviously 1. And so the total energy of a harmonic oscillator is proportional to the amplitude of oscillation. It's also proportional to omega squared, but we won't be so interested in that here. Well, let's compare that back to our energy. Intensity is, as we've seen, energy per time. Again, script A's are going to be areas. Sometimes you see this written as an energy, if I take our definition of intensity, and if I multiply and divide by delta x, then delta x delta t is just the velocity, and then a delta x is just a volume. In fact, it's the volume that energy that hits the thing is in. And sometimes you'll see that defined to be U sub E, which is the energy per volume or the energy density. And so sometimes you'll see these expressions. For light, this would be the energy density of the electric field that's in the light. And then V, of course, would be the velocity, which would be C. So sometimes you see that for light. Now let's go back to look at this case of a simple harmonic oscillator. Simple harmonic oscillator. Simple harmonic oscillator, one has the energy is proportional to the amplitude squared. And since this is energy per volume, if I had a bunch of these, I would have amplitude squared here per volume. But in any event, the energy density one expects to be equal to the energy, this amount, per volume. And so the energy density should be proportional to the amplitude of oscillation times the frequency squared. And the intensity is just that. And so we combine these two to see that the intensity is roughly proportional to the amplitude of the wave squared times the frequency squared times the velocity. For light, this is the amplitude of the light wave. The omega is the frequency of that light. And v, of course, is the wave velocity, but for light, that's the speed of light, c. Now then, let's look at a spherical wave. Spherical wave is simply a point source. So I have something here that's generating a wave. Maybe it would be light, in which case this P naught would be a constantly radiating light source. But the intensity naturally falls off as you get further away from an object. It becomes less bright. And you can see that here. The intensity when I met this along the sphere of radius 1 is P naught divided by the area, surface area of the sphere of radius R1. And that's just P naught, the area of a sphere is 4 pi r squared. And for the small sphere, it's R1 squared. I get out to this region. The intensity is the power divided by the area of this outer sphere, and that's just P naught 4 pi times R2 if R2 is the radius of this outer sphere. And so I can take the ratio of these areas, I2 to I1, and use these two expressions. This I2 is P naught over 4 pi R2 squared. I1 is P naught over 4 pi R1 squared. It was the same power source in both cases, and the 4 pi's go out. So these cancel out. And what you find is that essentially this I2 is proportional to the radius, inversely proportional to the radius squared, the distance squared. So intensity falls off as 1 over the radius, the distance from the light source squared. It satisfies a 1 over 8 r squared relationship. However, we've already said that intensity is also proportional to the amplitude of the wave times omega squared v. And so I can use that here. Intensity is proportional to a squared omega squared v. And I can also get the ratio of A2 to I1, the intensity at 2 to 1. And that's going to be the amplitude of the wave at radius R2 to the amplitude of the wave at radius R1. And I'm assuming we've got the same frequency, same color of light, and then the velocity is the velocity of light, so these go out. And if you look at that, it says that the intensity is at 2 is proportional to the amplitude of the wave at 2. And also we found that the intensity was inversely proportional to the distance squared. And if you string this out, if this is proportional to this and this is proportional to this, you should have that the amplitude squared is proportional to 1 over the radius, the distance you are from the source squared. Or taking square root, the amplitude has got to be proportional to 1 over the radius. And that's what we'll do. If I'm at a distance capital R away from the source of the light, then it's sinusoidal. I've got the propagating wave, k times the distance minus omega t. Could be plus or minus in general, but right now we're looking at outgoing waves. And I know that the amplitude out here has to be proportional to the radius, and so what I'll do is I'll take a constant A naught as a constant of proportionality. It's not really the amplitude. The amplitude is it varies with how far I am from the light source. And then the way you usually write this is just the amplitude of the wave times sine kr minus omega t divided by r as the wave function. It's really a spherical wave that's propagating out from a central source, and the radius here is the distance you are from the source. Now, if you look at a light source here, these are waves coming out from it. The spheres get larger and larger, and so this factor, as the light source gets as r increases, I see that the overall amplitude, this a over r, a over little r in this case, is going to decrease times this sinusoidal function. And so for spherical waves, water waves propagating out, the amplitude falls off here. So this dash curve shows you the amplitude of waves. The amplitude of the wave gets smaller and smaller as you get further and further away, and so the intensity of the light drops as well. The amplitude, though, falls off as 1 over r squared.